Yeah, common see that was clear because it was a bit tricky, and at the end of the class, I just failed to tell the correct thing. So I will just start with that again. But yeah, welcome to the third live session for this course, third tier live session. So I am Utpreksh, and we are attending the course Digital Circuits, which is being taught by Professor Shantanu Chattopadhyay. So this week I aim to discuss the problems based on combinational functional minimization. So you guys have already read about K-map and Boolean identities. So these are nothing but some properties and identities that will govern your Boolean number system that you have to follow in your computations. So these identities I hope you guys are clear with. So these are some of the Boolean identities. Yeah, so these are the Boolean identities, and we will discuss them one by one. So are you guys already comfortable with Boolean identities, or should we discuss them? I would say if you guys have some doubts in this, that we can discuss, because this will be again a repetition of what professor has already taught. Yeah, so if somebody is having some issue to listen, I am also typing these things in chat box. Yeah, so yeah, these are very basic properties, so I don't think we should spend a very long time on this. Rather, the important things that you should take care while solving these problems and related to Boolean algebra are the properties of Boolean identities, which are like duality that will help you to convert your um, what is known as min terms and max terms, so you can interchangeably convert them.
Sir, you can revise shortly, just for revision.
These identities, right?
Yeah, fastly, I mean, in short.
Yeah, so is there a specific identity which you guys would have had some problem?
No, we know.
Yeah, so the closure property for a number system would govern the fact that whatever operation you are going to do, what is happening in this? Just a sec. Yeah, so I will just try to discuss orally. There is some issue with this pen. So closure ensures that whatever operation you are choosing to do in your number system, the resulting number, whatever result you get, would again lie in the same number system. So like in the last some question in the last of the classes, we tried to solve a equality problem in which two numbers of different number systems we tried to equalize and find the values of x and y. So their one number system was from number system 3 and other was number system 7. So in that when we tried to solve, we were getting the solutions which were lying out of these number systems. So like for the number system 3, the numbers which are allowed would be only 0, 1 and 2. Whereas we were getting solution that was I think 7 I think. So 7 doesn't lie in this number system. So whatever equality we were trying to check or find the value for that just didn't satisfy the closure identity of number system. So in closure property of Boolean number systems, whatever operation you do, the result should be either 0 or 1, and this property ensures that you won't get something which is out of this number system. Then coming to associative property, this ensures that if you are having an order of operators, suppose there is a multiplication. So let's say there is x into y into z. So if you try to solve this, or you proceed to solve x into y and then multiply this by z, this would give the same result. But whereas, similar to what we have in our mathematical system, in which we follow a BODMAS rule, the operator precedence is there. But still, if you are careful of the operator precedence, then associative property takes over there also. Then commutative property ensures that your order of solving the Boolean problem or a Boolean operation doesn't change the result. So as we discussed here, x into y into z, or else you do x into y whole bracket into z, that would ensure that you will still get the same result. Then the identity property ensures that there is at least one number in your number system with which if you multiply your, suppose there is a number x in your number system, and if you multiply a number, and that will still give the same number as an output. So this identity for most number systems would be 1. And in our number system in Boolean, if you have just 0 and 1, so if you perform any x into 1, that will still give you x. So that is identity, or rather Boolean identity. Then there is something that is called as inverse. So inverse is a property in which there exists a number in your number system where if you do the addition operation, suppose you have x and you do some plus y, that should give you 0. So this is basically additive inverse, and in this case y should be minus x. So can you guys tell me whether you have an additive inverse for your Boolean number system where you have only 0 and 1? You can type in chat box yes or no. Yeah, you guys got the question, right? Either you can say for Boolean or natural number systems. Do they have additive inverse? You can type in yes or no, or you can unmute and tell if you have some answer. Okay, since nobody is answering, I will tell. Yeah, the additive inverses for these number systems do not exist because to have y equal to minus x for either natural numbers are nothing but the counting numbers that start from 1, 2, 3, and they go to infinity. So there, the negative numbers do not exist, and so you don't have additive inverse in these number systems. So even for your Boolean numbers, you don't have additive inverse. Then distributive property tells that if you have a series of operations that is occurring in one of your functions, that operation can be distributed over your whole function. So let me just make some space. So if so when you have a distributive kind of satisfaction in your number system, that would mean that if you have something like this, so you have this operator which is multiply in this case, this will get distributed over your previous operands. So that would mean that this would be still same as x into z plus y into z. So that just depends on you whether you want to directly solve this bracketed format, or you can simply distribute it to make it simpler for your understanding. So these were the basic properties that corresponds to your number systems. Then I guess you guys completed function minimization in your last week. So this week, till what part you guys have covered? Yeah, so earlier also we had been discussing that why do we require digital circuits in first place? And we came to conclusion that binary number system is a number system which is compatible with our computers that we can program. And from that, why do we really require function minimization? Why we cannot do it without minimization? So you guys might be having some clue because you have been attending the classes. So you can unmute and tell, or you can also type. So why is function minimization really required? I would like to know from you guys. To reduce hardware, okay. So yeah, Gaurav is right basically. So whenever you are dealing with digital circuits and its realization, you would be requiring to save space and also resources on your hardware implementation. So this minimization allows you to actually save space on that front and also to make your hardware less complex to deal with. And also, when you once minimize these functions, they would be really a bit more easier to understand and implement. I will just take a minute. I'm having some problem with my tabs. Uh, Yeah, so there are basically two or three types of uh, expressions in which you can write down your functions and try to minimize it. So out of them, there are basically three forms. So one will be your standard form, one will be canonical form, and the other will be your K-map or truth table format. So truth table and K-map are really just complementary to each other. So I will just explain in this slide in a bit. Yeah, so meanwhile, can you guys tell me how a product of sum or sum of product is finally implemented? So just you can give me the answer in terms of like what is the gate that you use as intermediate or what is the final gate that you would use. So if you are able to answer it, I would know that yes, you guys have already understood what the professor has taught you. Yeah, so what are the final gates in POS format, that is product of sum, and sum of product formats, the final gate that your function will pass through? So you guys are already aware with this, so I'm just asking directly. Yeah, so we are back. So, yeah, anybody? Yeah, so basically in product of sum and sum of product formats, you will be having some function and there will be some variables. Let's say there are some n number of variables and there are some functions, some black boxes, some gates will be there. And finally, before the final output, there will be still some black box, a gate, and you will be getting your expression either SOP or POS. So I want to know from you guys what will be this gate in case of SOP and POS kind of minimizations or expressions. So I've already pondered and given some time over this. So SOP is what? It's sum of products. So here sum is the keyword. So finally whatever function you're having there, this summation will be there. And whatever expression is there, that will be written inside this. I hope this kind of notation is clear to you guys. So since there is a sum and sum is nothing but, let's say there is something as a plus b plus c or whatever. So this sum is actually given by OR gate, right? You guys can just correct me if I am wrong at some point. That is okay. We can keep this interactive. So this signifies sum. So in case of SOP, if you ever encounter this summation and function written in this format, this signifies that this is given in SOP kind of notation. And complementary to that, there is POS, and here this means product of sums. And here the keyword is product. And product is done by AND gating. And this is OR gate. So you guys have covered these notations, right? SOP, POS during minimization. You can just type in yes or no. Okay, nobody's typing. Okay, so I will just assume that you guys know. So here for an example, I have just written down a truth table. So as we have discussed, there will be three basic forms for functions. There will be canonical form, there will be a minimized form, or else you can have your expressions. So this is just complementary to this. This K-maps and all will just give out the canonical form. Canonical minimized is there. Or else whatever you like wrote down, so that again goes for K-maps here. So this is a truth table, and this we will try to make a similar K-map. And how would we notify this function into a K-map? So here we will take all the ones, and the way we write this K-map is that the possible values of a that you are having for this variable, you will write down along this column, and for b you will write down along this row. So I am just trying to explain how a K-map is filled and what these boxes mean. So there are these our four boxes, box 1, 2, 3, 4. So you might have seen that they have some notation and you have to write down these ones or zeros at specific positions. So how do we decide these positions where to write them down? So if you're having A and B here and this box corresponds to 0 0 for both. So this will be 0 0 for both, and if you convert 0 0 to your decimal for our understanding, this will be 0 in decimal. So you just label it as 0. Then if A is 0, B is 1, this will be 0 1 in decimal and that will correspond to 1. So this box will be having the notation as 1. And for these our functions, similar thing we can write down 0 1. This corresponds to 2, this corresponds to 3. And if we encounter 1 and 0, so 1 and 0 in decimal will correspond to 2 in decimal, from binary to decimal. So this 1 0 will be actually 2, so 0 1 2, and the finally when we have both as 1, so 1 1 from binary to decimal will correspond to 3. So this will be 3. So as you see from the truth table, you have three values of 1 and one value of 0. So for zeroth position, we have to write 0, and for other three, as we have seen for 1 2 3, we have 1 1 1. So this is the conversion from truth table to K-map. So this is done only for two variables, but in actuality, K-map can be used quite comfortably till 3 to 4 variables. As you might have seen or encountered that if you try to write down a truth table for 3 or 4 variables, that would correspond to 2 to power 3 or 2 to power 4. That is 8 to 16 rows. 8 to 16 rows. So that is quite a bit to write down, whereas a table is far more accessible if you try to write down. So that's why K-map can be used alternatively to minimize between these two. So now let's jump to some questions. So these some of them might seem very trivial or easy for you guys, but still I would require you guys to answer this. So which of the following is true for Boolean algebra? So either it has only two operators, or it has only two values, or it has only two bits, or it can be represented in two number systems. So which of these are true for Boolean algebra? So you can just punch in the correct option that you think would be true for this. Gaurav is saying A, it has only two operators. Okay, we will discuss over that. So just for a hint, you might have seen or and not and these kind of gates or operations. So these are actually operators. So here itself I have written down 3. So A is definitely not the answer. Then Rifai is saying it has only two values. Okay. 0 and 1. Yeah, there are two values. Okay, so it has only two values. So this is true that you will get either 0 or 1. And you will try to give out your answers in that. And apart from that, D is also correct because it can be represented in two number system. Oh, sorry, it's not the correct one. If it is, it can be represented in two number system, meaning binary number system, then this would have been correct. But here it has two values, 0 and 1. So out of every Boolean algebra or a Boolean function, you will be getting only two possible values. It will be either 0 or 1. Then yeah, let's get into some simplification and minimization kind of problems. So here, what will be the number of rows in truth table for the function w plus xy plus xz plus yz? So for this, I guess, I hope this is an easy question for you guys. Gaurav is saying 16. Okay. So Gaurav says 16. Someone else would like to again punch in the answer? Okay, so the number of rows in a truth table is governed by 2 to power the number of variables. So here in our expression, whatever we have, so Komal is saying B, yeah, B16. So yeah, B is the correct answer. So if you are having a function here which is given by W plus X dot Y plus X dot Z plus Y dot Z. Here you can clearly see that we have W as first variable, X as second, Y as third, then Z as fourth. So you in totality will be having W, X, Y, Z, and this is your function. So this is the actual form in which you should always write down your functions so that you know that there are four variables. And this, in this case, 2 to power 4 will be nothing but simply 16. So if you were not having W in the first place, what would be the number of rows? So you guys already know the solution to this. Gaurav is saying 8, yeah, true. So if you just have X, Y, Z, whatever operation you do, so your truth table will be having 8 rows. So this was really quite simpler one. Then yeah, this is a very small part that your professor might have covered. So what would be the nature of expression PQ dash dashed P dash QR dash? What would be its nature? Nature, or if not nature, then what would be its minimized format or simplified one? So I will try to open it up and simplify here. And here the dash, I hope you guys know that this is nothing but complement. I hope this notation is clear to you all. So yeah, while you are trying to take a guess, I will try to open up this expression. So I will just denote it using F equals to PQ dash whole complemented plus P complement QR whole complemented. So the way we deal with these complements out of the brackets is in the way that when this complement gets inside the bracket, all your dot operations would convert to plus, and the variable that you're having, suppose if it was p and it is encountered by a dash, it will just become p dash. So this is the part of your Boolean identities that earlier is quite clear to you guys. So when I try to open up these complemented format, this will mean that p dot q dash becomes p dash plus q. So this first part of expression becomes this. Now we are dealing the second part of this expression. So here it will be p complemented again complemented. So complement of complement will give you the original variable, that is p. Then you encounter a dot. So dot is converted to plus. Now there is a q, and q is encountered by complement, so it becomes q complemented. Similarly, then again one more dot is there, that will become plus. It will give r, and since r is encountering the complement, it will be r complement. Now here we will try to group the similar variables. So p dash plus p plus q dash plus r dash. So I hope you guys know that for any variable, if it is added with its complement, that will always give out 1. And this is quite simple to see when you write down its truth table. So if you have a to be 0 and a, then a bar will be 1, a bar or a complemented. And if you just simply do addition, this will give out 1. And in other way around, if a is 1, then a complement will be 0, and this will become 1 plus 0, that will again be 1. So in this case, we actually have two complements addition, that will be 1 plus 1 plus r dash. This will again become 1 plus 1 will be 1, and 1 plus r dash will be 1. So this expression will always give out 1. So which of the options is now correct for this? Can you guys take a guess? So clearly P dash plus Q dash is not the answer. So Gaurav is asking if we use A complemented plus B complemented. Okay, and then you are just, okay, you are doing the reverse thing. Yeah, this also we can do. But whatever I have seen, this sum of product is a bit easier for us to understand. So and there is a chance of less chance of mistakes in that. So yeah, you can use this also. Reverse property is also true. So here B is not the answer. Fallacy simply means that if your output is always 0 or false, that expression or operation is known as fallacy. So this one is actually having 1 as output, which is true. So this will be either D, and so this will be both D and C, tautology. And tautology means if when your function is always having output to be 1 or true. So here C and D both satisfy the answers. So in last week, like I understood that some of you guys would like to use the art of just eliminating the wrong options. So I would say always try to check for every option that you are getting. Yeah, for saving time, and if you already know that there will be only one correct answer, the elimination will work. But in some questions, if you are having more than one correct options, just be very careful. And moving on, let's try to simplify this expression. Um, I I would like you guys to solve it, and I will solve it parallelly on this white space. And as you get the answer, just punch it in the message box. Or if you get some doubt or something, that also you can write it down, or you can just unmute and ask me. So I will just write this to be f equal to x bar y bar z plus x bar yz plus xy bar. So this I need to simplify. So as you guys remember, the distributive property is there in which the operators will be distributed and it will open up in this format. But you can go to the reverse of it also just to check whether it again closes down or not. So here in the first two expressions, I can see that x bar z and x bar z, this is common. So this I can just take as common, and then I can write down the remaining expression. So what remains will be y bar plus y plus xy dash. So here there was nothing common, so I just left out this expression. Then when I have this as outside in common, and then y bar plus y will be nothing but 1, as we already dealt with this property earlier. This will be simply x bar z plus xy bar. So this we were able to solve very quickly. This was a very short question. So here the answer seems to be B. I hope you guys also get this. So Gaurav punched in as B. Yeah, correct. Yeah, since this was a very short question, what I would like to get from you guys, can you write down its canonical form? This one only, sum of products. Just write down the total canonical form. Just for hint, I will tell you that this last expression is actually not in its form of either what you can define in truth table or a K-map. So to write down this expression in a truth table or K-map, we would require a Z. Here Z is missing in third form, this third part of this variable. So Z is missing. So I hope you guys know how to insert a Z. So what we are trying to do is we are trying to write down a truth table for this function. In third term multiply by Z plus Z dash. Yeah. So Gaurav is correct. Here what we can do is to write down this in a canonical format x y bar. This is nothing but 1. So this will become x y bar z plus z bar. I will just continue with the expression that we need to complete. So this will be x y bar z plus x y bar z bar. And if you just try to write down this in SOP format, that is sum of products. So this expression that we are having here is a sum of product. So here we just now to judge the positions, which positions these variables correspond to. So that we can easily do by saying that x is always corresponding to 1, whereas x bar will be 0. So this first expression that we are having, this will be 1, 0, 1. So 101 in binary would correspond to 5 in decimal. So fifth will be 1. So in truth table or in K-map, whatever are the locations for the value 1 that we always write down in SOP format. Whereas the second expression would become 100. So that in binary would correspond to 4 in decimal. Now this third term, this will be 001 and that would correspond to 1 in decimal form. And the final one, 011 in binary would correspond to 3 in decimal form. So 1, 3, 4, 5. So this was the minimized form, whereas we went backwards. So Gaurav has typed in 1, 3, 4, 5. Yeah, correct. That is true. Komal also got the same thing. True. So apart from this question, what we did, we also found out the canonical format. So you know that these forms are interchangeable, and as you are having the problems that you need to solve, so for hardware minimization, you always go for minimization. But if you need to denote this in K-map or in truth table for some reason, so that is also possible. You just need to know how to feed in. So this was sum of product form. So if it was product of sum, and if one of your variable, let's say again z was missing, so in that case, what we would have done is that we need to denote 0 there. So there 0 would have given by z dot z bar. So wherever your this z, yeah, z dot z bar. So wherever your variable is missing, you just need to use the identity, that Boolean identity you need to use, where if you in sum of product, if you multiply by 1, you get the same expression. Whereas in product of sum, if you just add by this one, the missing variable, still you get the same answer. So that you need to ensure to convert it again. Yeah, so now in this question, find the complement of function f equal to x in bracket y complement z complement plus yz. So what I need you guys to find is f bar. So that will be actually whole complemented in this way. So I will solve it in this slide. You also do it parallelly and type in the answer. So this is nothing but mathematics and properties for Boolean number systems that you should be knowing. So here again, as we had dealt earlier with the complement, so as this complement gets inside, this x will become x complemented. It will encounter a dot, so dot will become plus, and this remainder of expression we can write this down, and again we will do it in the next step. So this will be x bar plus, then y complement is encountered by the complement, it will become y, then dot will be encountered, this will become plus, then z complement will become z, and as we get a plus here, this will become dot, and again y is encountered, dot is encountered, dot will become plus, and z will become z bar. So this is something that we'll be getting. Then we will just open up the brackets. So y dot y bar plus y z bar plus zy bar plus z into z bar. So these dots you already know will be 0, correct? So this will be 0, x bar plus yz bar plus zy bar. So this is the f bar that we are getting. So it seems that whatever we are getting is not in our options. So here I think we only have the second part of solution in this. Okay, that is also not here. So the correct answer will be actually this. So if you have got this as an answer, you can just type in and tell me that yes, you have got it. Okay, Komal got it. Gaurav also got it. So yeah, here in this question, our answer was not in these options. So yeah, not always like try to back calculate from the options that you see. So this way it took some time, but still you will always get the correct answer. And it was not very complicated also, I hope. Then moving on, again this is a problem of minimization. So we need to find the minimized function. I think this is the same expression. Yeah. So we need to find the minimized form of f equal to x y bar z bar plus yz. So I will try to solve it. I don't think I have cross verified. So this will be again a new answer for me also. I want you guys also to solve so that if I go wrong somewhere, I can get that, yeah, I have gone wrong somewhere and you have done it correctly. So let's do this one together. Okay, I think there is nothing to minimize in this one. Sorry for that one. So we'll just move on to the this question to find the POS form, that is product of sums. So and also this is a hint that this actually signifies product, and if you encounter summation somewhere, that signifies sum of products. So you know in which system or in which expression you are dealing. So here we are dealing in product of sum format, and the function that we are having is actually a four variable function ABCD that is given by product of 1, 3, 5, 7, 8, 10, 11, 12, 13. So always write down first what you are having. Now we will try to draw a K-map for this. So this is a four variable function. So this will be a 4 cross 4 table. And as we already have uh, the way we notify different boxes, I will just write down that. Yeah, just correct me if I go wrong somewhere. Okay, even in the notations. So this will be 0, 1, 2, 3. This will be actually 2, 4, 5, 6, 7. This will be 8, 9, 10, 11, 12, 13, 14, and 15. So since this is a POS form, so wherever you are having this location of your function, you need to write down a 0 in your key map. So here we already have the locations, that is 1, so we will write down 0 at 1, 3, 0 at 3, 5 is a 0, 7 is a 0, then 8 is a 0, then 10 is a 0, 11 is a 0, 12 is a 0, and 13 is a 0. Okay, so we are having these many zeros here, and this is how the KMAP will look like. Now let's try to group it. So the way KMAP minimization works is minimization is that you need to populate and write down your KMAP in the first place, and after that you need to group them. So this grouping we usually do in powers of 2 to power n. Okay, so you either group it in a group of 2, 4, 8, 16, or whatever you will encounter. So we'll start from the largest number. So here a group of 16 is definitely not there. Then we will check if can we form a group of 8. So here if we see here is a group of 4, then there is nothing more than that. So the largest group that we can form here is will be this group of 4 zeros. Okay, so this we will form. And again, these K maps are actually rollable. So if you are having something here, and if there was a 0 here, just for an example, if there was a 0 here, then we could have formed a group of 4 like this also. So this K map is actually rollable. Yeah, I'll write it down again. So this group we had formed, there was a 0 here and there was nothing here. So here we will form this group of 4. Then another group of 4 is clearly not forming here. If there was a 0 here, then this could have been a group of 4, but we don't have a 0 at position 9. So now the remaining zeros, we will have to just make a pair out of them. So here this will form a pair, this 12, 13 will form a pair. Now this 8 is remaining. So now we'll have to use this 12 again to form a pair. So this is always preferable. So once these pairings are done, now you need to know what this groups mean or what you can write them down directly. So here the group of 4 that is here. So this when you see from this direction, you need to see which of the digit is actually changing. So here 0, 1 is changing. So I will also write it down what this actually means. So okay, we will arrive to that. I will just directly write it down like I'll just write down the individual expression for these zeros. So these will be A bar plus B bar plus C bar plus D. This will be your 1. Why are you presenting, man? Okay, try not to do that. Yeah. Then this 3 will be A bar plus B bar. This was 1 1 plus C plus D. Rahul, can you please stop doing that, man? You want to show the solution. Okay, let me tell you very clearly in the first hand that the solution that you are showing, that is actually for sum of products. Are you there, Rahul? You can either unmute yourself or you can also type in chat box.
Yes, sir.
Yeah,
Tell me, sir.
tell me.
Sir, this answer is correct.
The one that you have solved, that is actually sum of product form. That is not what
Yes,
have been
sir.
asked, right?
Thank you, sir.
Yeah, so what we are solving is for product of sum actually.
Sir, I'm not able to see your slide.
And now is it visible? So actually Rahul started presenting. So I would say first unmute, and if you want to show something, I will definitely allow you. Okay, now I think it is visible. So this is 1, this is 3. 5 will be A bar plus B plus C, C bar plus D. This will be 5. Whereas 7 will be A bar plus B plus C plus D. So this is what these expressions actually mean. So when you try to minimize and get to what this group of 4 would mean, so there you just need to take the expression or variable which is not changing its value. So here in this case, you can see when transversing through these boxes, A still remains 0 always, whereas B will change from 0 to 1. So you have to leave out the B and you just need to write A bar. Whereas when traversing in this CD direction in this row, when you are going in this row, here you can see that C actually changes from 0 to 1, but D remains as only 1. So this will be D. So this is what you will get when you simplify this box of 4. I hope I am correct. So this group of 4 will give A bar plus D.
Yes, sir.
Now we need to figure out what the other 3 boxes which are groups of 2 would mean. So that is also similar process. You need to check which of the expression is or which of the variable is actually changing. So that we will now do quickly because we use K-map because you don't want to use identities every time. And K-map is time saving, and also you don't need to always know the identities for solving, right? Earlier we tried to solve and minimize. There you need to know the identities, but here you can simply do it with these thumb rules. So now we will process the groups of 2. So first we'll go to the group of 12, 13. In this case, AB doesn't change. It remains 1, 1. So that will be A plus B. And in this case, C remains as 0. D changes from 0 to 1. So we will have to leave out D. So C will be 0. So it will be only C complemented. So this is one of the 3. Then again, we will take the group of 12 and 8. Here in this case, CD remains as same and here A remains same, but B is a variable which changes from 1 to 0. So this will only give out A plus C bar plus D bar. And the last group of 2 which is this one, that is 10 and 11. Here AB remains as 1 0, but D changes from 1 to 0. So only C remains as 1. So what we will get here is A plus B bar plus, and here C is not changing, so C. So these are the expressions that you get out from grouping of these boxes in your K-map for this function. So this pretty big looking function can actually be written down as, now the guys who are joining now, the class was from 3 to 4. So try to join earlier when we are actually discussing the questions. So now we just need to write down the groups, and since it is a POS, that is product of sum, so we need to just make a product of these all sums of individual groups and boxes that we had find out. So this will be the final expression that we will be getting. And since it was a POS, we had to write down 0 at every place. Now as somebody had shared screen between Ragul, I think. So Ragul, what you were showing, that is actually for this part. When somebody has to say something. Okay. So what Ragul was actually trying to share and show that he had solved in SOP format. So what he had shown was actually true for this question. So we had done the other part of it. I think I have just mistyped it. This is not a multiplication. This is actually summation. So I think it is already 4 and this is the last question. So we will just solve it in a hurry. So you already know what we need to do. So I will just write down a K-map. If you have some doubt, you guys can ask, because K-map is very useful, but again very confusing if you even miss a notation or something. So this is my way of doing it. I hope this is also helpful for you guys. So this is actually easy to remember what we had earlier written it down, but you need to do it correct. 14, 15. So here in SOP, you need to write down ones for your expressions which are true. So wherever we are having these numbers, we will write down as 1. So this will become 1, 3, 5, 7, 8, 10, 11, 12, 13. So this is actually the same expression, but in this case, when you are encountered with SOP format, here you have to write down ones and you have to make groupings for corresponding to that. So I will make groups with red color. So here, since these are the same positions, you will form the same groups. So this group of 4 will be there. Then this group of 3 is there, group of 2. Then this group of 2 is there, and this group of 2 is there. And again, here also, you need to see which variable is changing and which is not changing. So this, if you write down individual locations and then try to solve, you will still get the same thing. So here only A bar remains as same, A bar, and here this is SOP format, sum of products. So you have to write down these min terms, and min terms is given by, okay, Komal has punched in one answer. I hope you have got the correct one. So this will be A bar D. Then the groups of 3 remain, groups of 2, sorry, groups of 2 remain. So the group of 12 and 13, here you will be having AB, and the variable D is changing, so that we have to leave out, will be C bar. Another group, we have a group of this 12 and 8. Here CD remains same and A remains same. So A dot C bar D bar. And the last group that is formed by these positions 10 and 11. Here your A and B remains same and C remains same, but D changes. So this will be A B bar dot C. So I think Komal's answer is correct. Plus A B C bar plus. I think Komal, you have missed out at somewhere, or I might have missed out somewhere.
No, sir. Actually, I took different combination. That's
Okay.
why.
Yeah, yeah. So there can be multiple answers for it. That is true. So yeah, this will be the answer when you process this in SOP format. So SOP and POS are complementary to each other. So if you just put a complement here, you will get the answer that we got earlier. That will give out POS format. I hope you guys know this. So SOP's complement is POS and POS complement is SOP. So yeah, these were the questions that I wanted to discuss this week, and I hope you found these questions to be helpful, and I hope you guys also solved it. So, what I would like to know from you guys is till what part you have completed this week, so that I can bring in some good questions for discussion in next week's class.
Hello, excuse me, sir.
Yeah, Niketan, tell me.
Sir, in POS form, 1 is represent complement and 0 is represent uncomplement.
Which one? POS.
In POS form, 1 is represent complement variable.
Okay, okay. Yeah, I might have missed it. So that's why I asked to just keep correcting me because I just took out these questions out of random. So I'm just solving it with you guys. So that is good to know and good to discuss that that is the actual case. But again, you can always complement this POS SOP format, and if we are getting the same thing, then that one is okay, or else I have done the reverse way. So yeah.
Yeah. No, sir. I mean, means I have same doubt.
Hmm.
I mean, in POS, we took like complement of means for zero we consider one, and
Yeah.
for one so the expression will be changed, sir.
Yeah.
Means for
So.
example, AB means for example AB we are taking, and
Hmm.
A is like fixed 0 0. So
Yeah.
we have to take A like one. We have to consider one. And we are take means we took A bar, but we have to take only A.
Yeah. Yeah. I got you. So yeah, I think we took the
So,
reverse
sir,
expressions
if
for
you can,
this.
yeah, for
So
POS,
yeah, for PS.
SOP
Yes.
is correct, no
Yeah.
issue. Mhm.
So this will actually
Because
become.
sir, we have solved both. I mean, same problem we have solved, no. But the
Hmm.
only operator is change and other things we got same. But when
Yeah.
we solve, no, so in that time means total expression will change. Like,
Yeah.
I
Correct.
mean,
Correct.
complement. So
Yeah.
here we got
So
same thing.
yeah. So these will be
So
the.
next time, clear it.
Yes. So these will be the answers in the actual expression. So this one that I got was actually wrong. So thanks for pointing that
Yeah.
out. And yeah, good that you guys kept a note on it. And this week, till what part you guys have covered? If you guys have been attending professor's classes.
Actually, I am not aware about it because I haven't miss attend lectures because of some issue.
Okay, okay,
So I am
that's
not
fine.
updated.
Okay, okay, that's okay. So, anyways, I am just following his general timeline. So, till this week, I think this Boolean identities and K-map minimization was covered. After that, I think we will discuss gates, logic gates, and how do we minimize it. So these SOP and POS formats, these actually we can implement in gates, and this is the thing why we minimize it. So these various minimizations that we do is actually to implement it in hardware, and that we will see next week. And I hope the topic that we covered last week, which was floating point notation, that was clear to you guys. So even if you guys have some doubt in that, that we can discuss.
Sir, is there means saved video? I mean, if you want to see again, then
I
is
think
there link for that?
yeah, these all videos are getting uploaded to our respective YouTube channels. So from there you can
Okay.
again
So
do
can
it.
you share me?
Yeah, yeah. So
I
you
mean,
can just send me a mail on this ID. I will share the links. So you guys can take a note.
yes, sir, just wait.
Yeah, so this class is over. So next week we'll discuss on logic gates and how do we do the hardware implementation of the minimization that we had done this week. So we will discuss that thing in next week. And I would thank you all to attend this class. And if you have any further doubts or clarifications required, you guys can always mail me.
Okay, sir. Thank you.